What's up, cool people? This is section 1.7, radical notation, day number 2, applications. And what applications mean word problems. And now I know some of you, whenever a math teacher says, oh, guess what, we're doing word problems today, you're like, oh no, not word problems. But word problems are awesome because they give us meaning. They tell us why we're doing what we're doing in the first place. Without real life application, math is really, I don't know, math can be just kind of really boring without actual story, like why we're doing what we're doing. Now I know word problems can be hard, so that's why I like to use a strategy that I call knowns and unknowns. So, knowns and unknowns. So if you get your knowns and unknowns straight, then things get a lot more easy. So what we do know is we know that L, well, let me just read it first. The formula R equals 2 square roots of 5L can be used to approximate the speed R in miles per hour of a car that left a skid mark of length L in feet. What was the speed of the car? What was the speed of the car that left skid marks at 70 feet long? 70 feet long. So what we know is that L is 70 feet. And what we don't know is we don't know speed, which is in R miles per hour. If you can just keep track of what you know and what you don't know, then that will make things so much easier for you when you're doing word problems. When we've got a formula, it goes like this. R is equal to 2 times 5L, and L is going to be, what was L again? 70 feet times 70 feet. You put all that into a calculator, and it will give you approximately 37 miles per hour. There it is. Make sure that you do the 5 times the 70 first, and then take the square root. Next, how long must a wire be to reach from the top of a 14-meter telephone pole to a point on the ground 7 feet from the pole? Okay, so here's the pole, and we know here's that. Oh, this looks like a triangle. Let me draw it out in 2 dimensions a bit better. So, got a telephone pole, the wire, and the ground 7 feet from the foot of the pole. This is 7 feet. I'm just drawing a picture. That's another strategy. Just drawing pictures is a really good idea. Top of a 14-meter, not feet, meter. 7 meters, 14 meters. How long must the wire be? What we know is, what is known is that A, B, and C. What we know is that A is 14 meters. We know that B is 7 meters. And what we don't know is C. Now, just really writing down what we know and especially what we don't know is the biggest strategy I have. The most effective strategy is clearly defining what you know and clearly defining what you don't know. Give it a variable, give it a name. If we don't come up with C, if we don't name C, this is so important right here. If you don't give a variable name to what you don't know, then how are you going to solve for it? How are you going to figure out what it is? Well, we do know that A squared plus B squared equals C squared. That's the Pythagorean theorem, C squared, and so this will be 14 squared plus 7 squared is equal to C squared. Taking the square root of both sides, we get C is going to be equal to the positive square root of 14 squared plus 7 squared. We don't need to consider the negative side because you don't need a negative distance. And when you do that, you get something approximately 15.7, approximately, I'm going to round to the nearest meter, that's going to be 16 meters. Alright, so real life applications. When you see applications, when you see word problems, write your knowns and clearly define a variable for your unknown. Without knowing C, without just choosing the letter C, then you are unable to write this equation. So it's so important to declare a variable for what you don't know. Simplify, that is, multiply the fraction by something so that the denominator has no radicals. So the goal is here for us to have the denominator with no radicals. Why is that important? It looks nicer, but also it has some calculus applications. Calculus, the class that you'll take in a couple years, it becomes so much easier once you have no radicals in the denominator. So it's an important skill to have. Now, how are we going to have nothing in the denominator? Let's figure out what the denominator is. Let's split it up a little bit. 3 and then cube root of 25. Now, the way we're going to do this, the strategy is we're going to multiply the fraction by something. And that something in this case is going to be a denominator times a denominator, or a number times a number. What we really want is like 25 is 5 squared. What I'd really be most convenient would be to have 125 here. That way I could take the cube root and it would be a lot easier. So how do you go from this fraction to this fraction? What you'd have to do is you'd have to multiply by cube root of 5. And then 25 times 5 is 125. What do you do to the bottom? You have to do to the top. So let's multiply this by 5. 3 times 5 is 15. Cube root of 15. Great. Now when we go to do the next step, this becomes, the denominator becomes simplified to just 5, and the numerator is the cube root of 15. And that is our answer. The denominator has been rationalized. Alright, same thing here. We have to somehow get this, well, why don't we just multiply it by 7y? The denominator. If we multiply that by 7y, then the fraction becomes 7y in the denominator, which is what we want. We want nothing, we want no radicals in the denominator. Whatever you do to the bottom, you have to do to the top. So then we get square root of 21xy. Trust me, when you get to calculus, it'll be a whole lot easier if you don't have any radicals in the denominator. Next. So this here looks like, gosh, it looks like a mess is what it looks like. Well, what we need to do is we need to get perfect cube roots in the denominator. So 9 isn't a perfect cube root, but 27 is. 27. 9 will go to 27. B isn't a perfect cube, but b to the 6 would be, so b to the 9th would be. B to the 9th. I'd rather take the cube root of 27 and b to the 9th. So how do I get there? I'm going to have to multiply by the cube root of 3 and b squared. So I have to multiply the numerator. Whatever you do to the bottom, you do to the top by the same thing, 3b squared. So now we have the cube root of 48 times 3, 144. A cubed b squared. Great. I'll bet you we can factor out we can find a perfect cube factor of 144. What are the factor pairs of 144? 144, 2 and 72. 3 and... Well, there they are. I took some time just to write them all out. Let's find the largest perfect cube we can. Now, I know if this were... Yeah, oh, here's one. 8. Perfect cube. Any others? Any larger ones? Nope, that's the largest perfect cube factor of 144. So, what I'm going to do is I'm going to split this up. Cube root of 144 is going to be 8, and then cube root of 18, because 8 times 18 is 144. And then I've got a cube root of a cubed, and then a cube root of b squared. The denominator simplifies beautifully. In fact, we've arranged it to do so. This is what we absolutely need. Good. Now let's simplify the numerator a little bit. We've arranged the 8 to be here so it could simplify, and the a to be here so it could simplify. So that means we just get 2a, and then cube root of 18, and recombining b's, we get b squared, all over 3b cubed. The next one here you can see is there's 2 radicals here. How are we going to get those radicals out? Well, one thing you can do is you can multiply the numerator and denominator by the denominator's conjugate pair. What do I mean by conjugate pair? Well, here are conjugate pairs. These 2 are conjugate pairs. These 2 are conjugate pairs. These 2 are conjugate pairs. You can notice that the only difference between conjugate pairs is that the one binomial has a addition and the other one has a subtraction. So we're going to do this. We're going to multiply this fraction by its conjugate pair. So you can see the conjugate pair would be 3 and 5, but instead of subtraction, we're going to have addition. Whatever you do to the bottom, you got to do to the top. So square root of 3 plus square root of 5. All right, when we multiply, we get square root of 3 plus square root of 5. Now the whole reason we chose conjugate pairs is because you get first square root of 3 times square root of 3 is 3. You get outside and inside cancel. Square root of 15 and positive square root of 15 is the cancel, and then you get, oh, well, I should just write it out. First, outside, inside, and last. So this simplifies down to, because these cancel, because you arranged them to cancel, you chose a conjugate pair so they would cancel, 3 minus 5, which is negative 2. That's your answer. It's the same value. In fact, if you type these into the calculator, you would get the exact same decimal value for both the start and the original. But the great thing about the final product here is that there's no radicals in the denominator, which is what we need when we get to calculus. Here, let's multiply by the conjugate pair of the denominator. Again, conjugate pair would be square root of x, and 2, the only difference would be subtraction. Square root of x minus 5. Nope, undo. 2. Whatever we do to the bottom, we do to the top. 2. So now, when we FOIL the top, we get first, that would be x. Outside, we get minus 2 square roots of x. Inside, we get minus 5 square roots of x. Lasts, we get positive 10. FOIL. First, x. Outside, negative 2 square roots of x. Inside, positive 2 square roots of x. And last, negative 4. simplify. We've got some like terms. In the denominator, they actually cancel out. And so in the denominator, we're just left with x minus 4. In the numerator, we have x minus 7 square roots of x plus 10. Alright, good people. So I realized that I left you without something to do here, but that's fine. What I'd like you to do right now is get started on your assignment 1G2. Just do the first problem. Maybe write down the whole problem set in your composition book and just do the first problem. See you in class.